Hi, and welcome to the second video in the series on projectiles from the Year 2 Mechanics course. And in the first video we looked at the basic ideas and this idea that we can split the flight of any particle into horizontal and vertical components. And of course if we can do that, then clearly we can use vectors to describe the horizontal and vertical components as well. So let's have a look at how we can do basically exactly the same as we've done before, but this time just describing things using vectors. So we've got a cannonball being fired at a ship from a castle, and we've got some information about how far the ship is from the base of the castle, how high the castle is, and all this kind of stuff. And we've got to work out whether or not the cannonball is going to hit the ship. So, off we go. There we go, there's our cannonball. Is that going to bash into the ship? Well, let's first of all deal with SUVAT, and because we're dealing with it in vectors, we don't need to separate out into horizontal and vertical. We can just deal with the whole thing in one go. So let's have a look at what we've got. So our displacement is 225i plus 26j. You'll notice it says in the question relative to the base of the castle. So we're taking the base of the castle, this point down here, as essentially being our origin, and everything is going to be relative to that. Okay, what else do we know? We've got u, which we don't know at the moment, so we'll just kind of describe it as that value there. Velocity we don't know at that point. Acceleration just in one direction, so that's just minus 9.8j because it's just happening in the vertical direction, and t at that point is 5. So let's work out what u is, because we're going to need that. We're going to need the initial velocity to be able to do anything else with it. So off we go, and as I said, we're dealing with things in terms of relative to the base of the castle, so we just need to do a little bit of adjusting as we go along to take that into account. So here we go. Right, that's what we've got at the moment. And if we go for s equals ut plus half at squared, so s being the displacement, which is this thing here, so we've got the 225i plus 26j equals u times t. So u we don't know, that's the thing we're looking for, plus half at squared. And then we've got this extra thing that I'm adding on because the cannonball's been fired from 28.5 meters higher than it would have been if it had been fired from the ground. So this thing is higher in the air than it would have been if it had been fired from ground level. It's 28.5 meters higher than it would have been if it had been fired from the base of the castle. So that's why we've got this extra adjustment figure on the end. Because this displacement value here, the location essentially of our cannonball, is what it would have been if it had been fired from on the ground, plus the extra 28.5 meters. So that's our adjustment. So what we're going to do is just do a bit of tidying up, and all I've done is just take these bits here, all components in terms of j, so just tidy those up a little bit. And so now what we've got is 5u is 225i plus 120j, so we've just taken the 94j over to the other side, do a divide by 5, and there we go, we've got our initial velocity in terms of horizontal and vertical components. So that's that first bit done. Now we need to see how far from the castle the cannonball is when it hits the sea, i.e. will it hit the sea 270 meters away from the castle. So here comes our SUVAT bits and pieces again. Now this time I'm going to do it slightly differently, because for the displacement I know something. I'm going to model it as if we're taking from the point where the cannon is fired, because at that point we know that we're 28.5 meters below that level there. So when it hits the sea, we've got a vertical component minus 28.5. And what I'm interested in is this horizontal component here. We've got our initial velocity, which we calculated from the last part of the question. Our velocity at the point the cannonball hits the sea, we don't really need that bit. We've got I and A, and T is the thing we're trying to find out, so the point in time at which it hits the sea. So let's deal with this one. So s equals ut plus half at squared. Put all my bits into that. So we've got s equals, there's ut, and there's the half at squared. And now what I'm going to do is I've just tidied that up a little bit on the right hand side. So we've got all my horizontal components, and the only horizontal component is this bit here. And we've got this bit here, the 24t and the minus 4.9t squared. That's our vertical components. Now, the reason that's useful is because what we're going to say is, well, we know that if this bit on the left is going to be equivalent to this bit on the right, we can equate our horizontal components, and by looking at that, we can say that, well, u is going to be 45t. And if we equate the vertical components, we've got minus 28.5j has got to be equal to 24t minus 4.9t squared. Now, in order to calculate that horizontal distance, we're going to need t, so we can get that from this equation here, because t is our only variable that's left in here. So let's turn that into a quadratic with a 0 on the left and do some solving, and we know now that the cannonball hits the sea after just under 6 seconds. So let's take that 5.88 and plug it back into u, which is the thing that we're looking for, that horizontal distance, and there we go, u is 264.6 meters. Now, final thing we've got to do is answer the question, and the question was, will the cannonball hit the ship? Now, at the time I was writing these PowerPoints, I was watching Game of Thrones, about 10 years after everybody else was watching it. So there we go, we've got good old Jon Snow. Will the cannonball hit the ship? And who was the person who came up with all the answers and all the clever stuff in Game of Thrones? Clearly it was Tyrion, looking a little bit sleepy in that particular cartoon, but there you go. Well, his view is we can answer this in one of two ways, and sometimes this does happen in the exam questions. As long as you justify your answer and it's sensible, then you can answer yes and no to this. So let's just have a think about it. Our first answer is clearly going to be no. We're told that the cannonball is going to hit the sea 264 metres away from the ship, but the ship is 270 metres from the castle. But the alternative says, well, it might. We're modelling all these elements as particles, so the cannonball, the ship, the castle. So it might not be the most accurate model in the world. So, for example, are we, is the cannon precisely 270 metres from the ship, or is it a little bit more inland? Is the sea level, is that, is it bobbing up and down, or is it flat? The ship, is the middle of the ship the 270 metres, or is it 270 metres to the prow of the ship? Because when we model things as particles, they don't have size, but clearly a ship, a cannonball, a castle, and all these things do. So you might say, well, 264.6 metres, that's pretty close. So you could answer, well, we could potentially have hit the ship. So as long as you justify your answer intelligently, then you can answer it either way. Right, so one more question that I'm going to have a look at in this video when we're talking about vectors and projectiles. Again, an exam style question. Now, bottom line is it might be set up as a vectors question, but if you want to separate things out and deal with it independently, it really doesn't matter at all. You've just got to react to how the information is given to you and essentially just try and find the answer to the question. So here we go. We've got a cricket ball again being hit from a point 0.9 metres above the ground, so we're going to have to think about that when we do a bit of adjusting. And we've got a whole bunch of information. It's 3 seconds to travel from A to B. We've got the distance OB is 57.6, and we've got an initial projection of this vector PI plus QJ. So, on we go. First part says find the value of P, given that the ball is taken 3 seconds to get from A to B. So we know that that 57.6 is just the initial speed times by time. So in the horizontal direction, I'm ignoring the vertical, just look at the horizontal, and I've just picked that P as being the horizontal. I'm not worrying too much about other parts of it, so it's as straightforward as going, well, that's going to be P is 19.2. Nice and straightforward. On we go to part B, show that Q is 14.44. Try again. 14.4. So this time I'm just going to look at it in terms of the vertical components, and we know that because it's projected from point A here, its vertical displacement at point B is going to be minus 0.9. So we can put that in, and I've just picked out Q as being the vertical component of the initial speed, and then everything else is as it is, and this bit here, this is our t squared because we knew t was 3. So all we've got to do now is solve an equation in terms of Q. There we go, and it does turn out as we wanted. Q is 14.4. On we go to part C, find the initial speed of the cricket ball. We've now got our value of P, we've got our value of Q. We want speed, magnitude of velocity, we've seen this a few times already. Bit of Pythagoras, and away you go. So it's speed 24 meters per second. And then part D, find the exact value of tan alpha. So the angle of projection. So bear in mind, we're not actually being asked to find the angle, we're being asked to find the value of tan alpha. So clearly that's just going to be a little bit of trig. So we've got the vertical components, the 14.4, divided by the horizontal component, that gives us 10 alpha, and bang that into a calculator, and the calculator will do a bit of simplifying for us, and we realise that 10 alpha is simply just 3/4. On we go. It says find the length of time for which the cricket ball is at least 4 meters above the ground. So here we go again. So we've got our vertical components. So there's the 4. And again, this bit here is what we would have it been projected from the ground. But because it's been projected from 0.9 meters above the ground, I've added on the 0.9 to adjust for that. And so that becomes a nice simple quadratic. And we can bang it into the calculator and get our values. Always watch out for these ones because it's not saying find the time at which it's 4 meters above the ground. It's finding the time at which the ball is above 4 meters. So what we need to do here, and this catches people out, it's dead simple marks, but also easy to drop if you're not reading the question. We've just got to do the subtraction to say, well, okay, it was above 4 meters for just under 4.5 seconds.